Hello everybody and welcome back to Calculus with Professor Val Lockman at Frederick Community College. In this video I will talk to you about the basic rules of differentiation. And if you follow the textbook that we're using, this would be section 3.3. In the previous lectures we discussed computing derivatives using the limit definition, right? So remember, you would set up your difference quotient, you would take the limit as h goes to 0, do some algebraic steps, simplify it, and come up with a function of x. Now in practice, this is not how we compute derivatives. There's a quick way to compute all of those derivatives without using the definition. So that's what we're going to do in this lecture. Okay, we'll start with the derivative of a constant, and it says the derivative of a constant is 0. This should make sense graphically because let's say you have a function that's constant, and it could be anything. Let's say you have y is equal to 4. The derivative tells us how the function is changing, right? What is the rate of change? But this function is not changing. It's 4 for every value of x. The slope of the tangent line is 0, right? So the derivative of 4 is 0. Okay? It doesn't even have to be a positive number. It could be a negative number. So d dx, let's say of negative 10, that's still 0. What other things can happen? Let's say we have d dx of a fraction. And that's still 0. We could have irrational numbers. d dx, let's say 3 pi, and that's also 0. And let's give another example of a number that's negative and it's irrational, so something like negative e squared, and that's still 0. All of these functions represent constant functions, right? Yep, so the derivative is 0. Let's take a look at the next rule. The next rule says that if I have x raised to a power, then to differentiate it, I need to bring the power down as the coefficient and then reduce it by 1. So how would I apply this? d dx of, let's say, x to the 5th. It is 5 times x. 5 minus 1 is 0. Okay. My power does not have to be a whole number. It could be a fraction. So let's say x to the power 3 over 2. And I'd like to differentiate this function. I'm going to bring 3 over 2 down. And what happens here? So 3 over 2 minus 1, that would be 1/2, right? So my final answer is 3 over 2 times x to the power 1/2, which is square root of x. Okay? Let's see. We could have negatives. Let's say we have x to the negative 7. The rule is still the same. We're going to bring the negative 7. So keep in mind that negative doesn't disappear. Okay? So minus 7 times x to what power? Negative 7 minus 1, that's negative 8. Okay? And let's see, what else can we have? Let's say we have something like this, d dx, and x is raised to the power 1/2. The rule is still the same. We're going to do 1/2 x to the power, what? 1/2 minus 1, that's negative 1/2. So over here we see that the power changed from positive to negative, and that can happen, and there's nothing wrong with that. All right? So this is a very fundamental rule, very basic, that we will use all the time. Many examples will have some sort of x raised to a power. So that's how we would do the derivative of a function like that. So let's go ahead and take a look at the next rule. And this one says if I have a constant times a function, how do I deal with that? Okay? What basically we're going to say that we can pull that c out. Okay? Pull the constant out and then do constant times the derivative of the function. Okay, so let's go through some example. d dx, let's say 10x cubed. I can take the 10 out times x cubed. That would give me 10 times what? 3x squared. And we can multiply 10 by 3, so we get 30x squared. Okay? A common mistake that I see sometimes, students say, oh, but the derivative of 10 is 0, so 0 times this should give us 0. You're right, the derivative of 10 is 0, but the derivative of the product is not the product of the derivatives. Okay, so we're going to talk about what we do when we have a product of functions, and that's going to be in the next section. Okay, if it's just a constant, just pull it out. It will make your computations a lot simpler. All right, let's do a couple more examples. d dx, let's say we have negative 1/4 x to the 8th. Okay, this is negative 1/4 d dx of x to the 8th. That's negative 1/4 times power rule 8 x to the 7th power. Okay, and we can simplify this, right? So this would be negative 2 x to the 7th power. Okay, so let me run through this real quick. This is a constant. It can be pulled out. Now I take the derivative of this, negative 1/4, 8x to the 7th, simplify. Here's my final answer. Let's do one more of these examples. Let's say I have 6 times x to 1/2. Again, I'm going to pull out the 6, d dx of x to 1/2. It's 6 times 1/2 x to the power negative 1/2. 6 divided by 2, that's 3. 3x to negative 1/2. Or if you really like, you can write it like this. Okay, either way, they're the same thing. Okay. Good. So here we have the first 3 rules that were covered. Let's take a look real quick. Constant rule, the derivative of a constant is 0. Power rule, the power comes down, gets reduced by 1. Constant multiple, the function multiplied by a constant. We can pull out the constant. And now one more rule. It says the following. If we have f and g that are differentiable at x, then this derivative of the sum is the sum of the derivatives. And this, of course, extends to finitely many functions. You don't have to have 2. You can have as many as you want. You can have 5, 10, finite number of functions in sum, and of course difference. So let's make sure that we know plus or minus is okay. And then for finitely many functions. Okay. All right, let's take a look at some examples here. d dx, let's say we have a function that looks like this, x cubed minus 2x plus 7. We can differentiate each one of these terms and then just add them. So this is 3x squared minus 2 plus 0. Or just 3x squared minus 2. Okay, let me go ahead and do this minus 2 separately. So negative 2x prime. Remember, another way of denoting the derivative is just say prime. Okay, it's negative 2 times x prime. Okay, but remember what x prime is. Okay, x is just x to the first power. So negative 2 times 1 x to what power? 1 minus 1. 1 minus 1 is 0. X to the 0 is 1. So this is negative 2. Okay? So here's one example of how to apply the derivative of something. Let's do one more, and you see that they're not very complicated. So let's say you have something like this. 4x to the 1/2 plus 3x to the 10th minus 5 pi plus e squared. Okay? I'm going to find the derivative of this. Okay, it's the sum of the derivative, so it's 4 times 1/2 x to the power negative 1/2. Here, 3 times 10 times x to the 9th. This is a constant, and so is this. Even though there is a power there, it's still just a constant. So this is plus minus 0 plus 0, right? Okay, this can be simplified to 4 over 2, that's 2. X to the negative 1/2 plus 30 x to the 9th. Okay, these two are constants. All right, we've covered the first 4 rules. Let's keep going. Derivative of a polynomial function. This is just combining all of the rules above. I'll give you a couple more of these. So let's say you have y is 4x to the 5th minus 2x cubed plus 7x minus 10. Okay? You can say dy dx, or y prime would be 4 times 5, that is 20, 20x to the 4th. 2 times 3, that's 6. Reducing by all my powers by 1. Plus 7 and minus 0. So that is my derivative. Okay, let's do one more. Let's say I have a polynomial that's not in terms of x. Okay, let's say we have something in terms of t. Okay, negative 3/4, say x to the 6, t to the 6, plus 5t to the 4th, minus 3t squared, and plus 10. Okay, I have a 6-degree polynomial in terms of t. The rules don't change. It's just a variable. So what is this? Negative 3 over 4 times 6t to the 5th plus 5 times 4t cubed minus 3 times 2t to the first power, and the derivative of 10 is 0. So my final answer, well, let's see, what can we do here? So 2 and 2, so what is this? Negative 9 over 2 t to the 5th plus 20 t cubed minus 6t. Okay? All right, so that is your derivative of a polynomial function. Basically, we're just combining all of the rules that we've learned so far. All right, let's move on to the next rule. What do we do with functions that are exponential? Exponential, where you just have e, which is the base of the natural log, raised to the power of x. Then the derivative is really nice. It's just the function itself. Okay? So what examples we can take a look at? So let's say we have d dx of 4e to the x. That's just 4 times d dx e to the x. The derivative is itself, so we get 4e to the x. Okay? Let's say we have something like this. 3x to the 5th minus 2e to the x. Okay? This would be 3 times 5, x to the 4th, minus the derivative of e to the x is e to the x minus 2 times e to the x. So that gives us 15 x to the fourth minus 2 e to the x. All right? Now, I'm going to give you a quick warning here. This rule is good only if you have e to the x. For example, if you have something like this, so this does not apply to examples like this, e to the power x squared, let's say, plus 4x, or e to the power x cubed minus 2, okay, or e to the power some function of x that's not identity, okay, so f of x is not equal to the identity, okay, so some more complicated function than just x. We're going to learn how to deal with this situation, but please make sure that you don't do this. So the derivative of, let's say, e to the power 4x plus 1 is not e to the power 4x plus 1. Okay? And again, I'm going to emphasize this is only true if you have just e to the power x. Okay? Also, the base has to be e. Okay? Not true for all other bases. Okay? So, meaning what? The derivative of 5 to the x is not 5 to the x. Again, we're going to learn how to deal with this situation a little bit later, but for now I need you to know that that's not how we're going to be dealing. Okay? So the examples that you'll see in the next few weeks will be just e to the x. Okay. We can also talk about higher order derivatives. So let's say I want to differentiate my function. Here's my function. I want to differentiate it one time, and then I'm going to differentiate it again, and then maybe one more time. So this is my function. This one we would call first derivative, second derivative, third derivative of the function. We can also have nth derivative, some abstract enumeration, okay? Another notation that you might see, so let's say you have a function, you might see something like dy dx. Second derivative would be d squared y dx squared. Third derivative, d cubed y dx cubed, and so forth. Nth derivative, the notation will look like this. In this particular class, we would only go maybe up to 3 at most, but you should know that you can differentiate function as many times as you wish, as long as it's differentiable, of course. So let's just go ahead and do a quick example here. I'm going to pick a polynomial function. So let's say my function is 4x cubed minus 2x squared plus 7x minus 5. So the first derivative of this function would be 4 times 3, that's 12x squared. 2 times 2, that's 4, so minus 4x plus 7. This is my first derivative of f. Second derivative would be the derivative of the first derivative, right? So this would be 12 times 2, that's 24x minus 4. And plus 0, right? So you can skip that 0. What about third derivative? Third derivative would be just 24. And if you really want to, you can find the fourth derivative. And that's 0. The derivative of a constant is 0. Okay? So that's the notation that you guys should feel comfortable with, and just differentiating function one step at a time, right? Let's say you ask to find the third derivative of the function, so just keep doing this process. Okay, so now that we've done all of the rules, let's take a look how we can solve different problems. So constant rule, that's done. Power rule, constant multiple, sum or difference. We know how to differentiate polynomial functions. We know what to do with e to the x. And we know that we can find more than one derivative. So now we're going to apply this knowledge to find the equation of the tangent lines at a given point. And in this case, we don't need to worry about computing the derivative with the long limit definition. Okay? So I want to find the equation of a tangent line for all of these points. So -2, -1, and 0, and the same function. So I have a cubic polynomial here. So let's start with finding the derivative itself. So y prime is, what do we have here? It's 6x squared minus 6x minus 12. This function right here describes the rate of change for the original function y. Okay, so the quadratic function tells us the rate of change of the cubic polynomial. Okay, so let's do the first one. A is equal to -2. How would I do this? I need to find the slope and a point, right? So what is the slope? The slope of the tangent line is the derivative. So y prime evaluated at -2. 6 times -2 squared minus 6 times -2 minus 12. Okay, let's see what I get. I get positive 24. This is my slope. Okay, that's the slope of the tangent line, which means at that point, the line will be increasing with a really, really steep slope, right? 24, that's relatively big. Okay, the value of the function y evaluated at -2. Okay, let's see, when I put this in, I'm going to get 0. That is my point. My point is -2, 0. And we're going to check all of this using a graphing utility. Okay, so now I need to put it all together. Let's see, what are we doing here? So this is y minus 0 is equal to 24x minus -2. That gives us a plus. So your equation of the line is y is equal to 24x. Once I simplify it, I'm going to get 48. That is my equation. Okay, let's go ahead and graph it to make sure that we are on the right track. Okay, I'm going to go to Desmos. I'm going to type in my cubic function, which is 2x cubed minus 3x squared, right? Minus 3x squared minus 12x plus 4. Okay, you can go ahead and put that point in there. So the point was -2, 0. Yes, there it is. You can already see that, yeah, I'm going to have a tangent line that has a relatively steep slope. Let's go ahead and make sure that our equation was correct. So the equation that we came up with was y, is equal to 24x plus 48. Plus 48. And there you have it. Okay, you can see that it's a tangent, right? You can zoom in and out to see that you get a tangent. Okay, good way to check if you've done it correctly. All right, so that's that for a is equal to -2. Let's go ahead and do problem 2, where we have which one? Which should we pick? Let's go with -1. Let's see what happens there. So for a is equal to -1. Okay, f of -1, you can compute that. So evaluate the function at f1. I'll call it y. Y of -1 is 11. So my point will be -1 for x, +11 for y. It's the point on the cubic polynomial. Then I need to evaluate my function at -1, my derivative, not the function, right? So 6 times -1 squared minus 6 times -1 minus 12. This gives us what? This gives us 6 plus 6 minus 12, that's 0. This tells me that the slope is 0. This should be a horizontal line, right? Okay, what kind of line? Y minus 11 is equal to 0 times x minus 1. But that simplifies to y is equal to 11. Okay, let's go back to Desmos. My point was -1, 11. Let's see where it is. Let's get rid of this guy for now. Okay, here's my point. Well, let's go ahead and label it. So yes, it looks like the tangent line to this point, at this point, will be the horizontal line. Which one? Y is equal to 11, and that's what we found. Okay? So again, always use or try to use a graphing utility of some sort to check that you do correct computations. Okay, one last thing. Let's see. Problem 3. A is equal to 0. F of 0 is 4. You can compute that. So my point is 0, 4. Here I'm going to go a little bit faster. Now we've done these problems. So f prime of 0, I get -12. Negative slope, this tells me that the line will be going down like this, right? Okay, putting everything together, y minus 4 is equal to -12 times x minus 0. Okay, this simplifies to y is equal to -12x plus 4. That is my equation. Okay, let's go ahead and check this one as well. Okay, I don't need these guys for now anymore. Let's see, what was the point? The point was 0, +4. Okay, yes, there it is. Let's label it. 0, +4. I already see that the slope should be negative. Okay, let's go ahead and add our equation. Y is equal to -12x plus 4. And it's a perfect tangent to the point at this, on this graph. Okay? So that's how you can check that you're doing correct computations. Alright, finding equations of tangent lines, that's your application for this particular section. Alright, thank you for watching.